Okay, so the first derivative we have been finding, it indicates where our function is increasing and decreasing. It helps us find our critical numbers. It helps us find our local mins and maxes. So now we are going to be talking about something related to the shape of a graph we've not talked about before. We've never had the opportunity to do this because you didn't know about derivatives. We're going to talk about what's called the concavity. The concavity test uses the second derivative. So again, that's the derivative of the derivative. If the second derivative is positive, so that's this one, we graph or we can say that our function is concave upward. I say the cup is up. So if our second derivative is positive, then our cup is up. It is concave upward. All of our tangent lines are under the graph. Okay. If our second derivative is negative, then our graph is concave downward. Our cup has been flipped upside down, or it's showing a frown, or it's upside down, or I don't care what you say. But in this particular case, all of our tangent lines are above the graph. We've never cared when we've graphed it about the curvature. You just kind of drew the graph and whatever happened, happened, okay? Now we can be very specific. Does it curve concave up? Does it curve concave down? What is the curvature doing? Which we haven't done before. So when we do first derivative and we do that plus or minus chart, it tells us where our function is increasing and decreasing. We can find local mins and maxes. If we do the second derivative, we make a plus or minus chart. The change in concavity indicates, and I'm going to use this abbreviation right here, it indicates what I abbreviate IP as inflection point. So an inflection point indicates a change in concavity. One of our functions that has this occur, one of our simple functions that we've known for quite some time, you might remember our parent function of a cubic has a change in concavity or an inflection point at 0, 0. If you look at the down left side, that has a concavity where the cup is upside down, but the top right, the cup is right side up. So the curvature is changing at 0, 0 for the parent cubic function. So now we have to be even more specific about our graph. Is it curving upward or downward? What is the concavity telling us? So we have even more tools to make our graphs more accurate. So let's take a look at this particular graph. It says in figure 8, it's showing the population graph for cyprian honeybees raised in an apiary. How does the rate of population increase change over time? When is this rate the highest? Over what intervals if P is upward, concave up and concave down? So how does the rate of the population increase over time? So the rate of change of anything is the slope of our tangent. So let's just think about the fact that if we were to graph our tangent lines, there's a spot about right here where our tangent lines are under the graph, and then our tangent lines start to become over the graph. So let's just kind of pinpoint its approximate location where that happens, okay? So if we look at our graphs, all of our tangent lines have positive slopes. They're always, it's an increasing function. Look, tangent line's positive, positive slope, positive slope, positive slope, positive slope, positive slope. But here the tangents are under the graph. Here the tangents are over the graph. So I'm going to shade this side of the graph one color. That part of the graph is concave down. And I'm going to shade this side of the graph another color. And this side of the graph is concave up. So our cup is up. Think about the fact is if it was a full cup, it could hold our cereal and milk. Here our cup, our bowl is down. It has been flipped upside down. You can't put anything over. So if the tangent lines are below it, if our tangent lines are below it, it's concave up. If our tangent lines are above it, it's concave down. So this little point here is called an inflection point. It happens, I'd say, really close to 12 weeks, maybe 11 and a half or something like that. Over what intervals is P concave up and concave down? So we can say that when time is between 0 and we'll just call it 11. It was concave up, and I'll just say CU for concave up. And when time was from 11 to 18, it was concave down. So that inflection point, let's say, happens at 11. When was the rate the highest? We just have to look at the slope of the tangents. You can see that they get super high really right before that inflection point. So that inflection point technically has what's called a vertical tangent line. And so that's kind of what indicates that we see that switch over. Okay. So let's talk about how you can also use the second derivative test to find maxes and mins. So if the second derivative tells us that when it is negative, it will be a cup flipped upside down, wouldn't that indicate that our point that we have found in question would be at the top of the cup? It would be a local max. So it's kind of the opposite of what we think. If the second derivative is negative, our cup is upside down, that's a local max. If our cup is flipped up, then we have a concave down section, but that would be a local minimum. So you don't have to do a plus or minus chart. What you can do is take the first derivative. Is it that first derivative? Find those critical numbers. Plug those critical numbers into the second derivative. If they are positive, you found a local min. If they are negative, you found a local max. You never have to draw the graph. You never have to do a plus minus chart ever. If the first or second derivative is undefined or 0 at that spot, you might have found an inflection point. So, we can use the second derivative and concavity to actually locate maxes and mins. So let's draw a graph that fits all the categories that they want here. So the values that I see for my x's, okay, the values that I see for my x's are 1, -2, and 2. So let's make this -1. Let's really kind of stretch it out like that. And then the only y values that I really see, you see some infinities and stuff, but I do see a y value of -2 and a y value of 0. So I'm going to really kind of stretch that graph paper out a little bit. Now, if you were to read this problem and do this problem on your own, instead of doing it with me, our graphs might look very different. but still have this exact qualities we need, okay? So note, there's no exact answer to this problem. Your answer should have these qualities, so should mine. Okay, so let's look at our picture. Let's see what our first little bullet tells us. Okay, so this is about the first derivative. So our first derivative is positive, so it's increasing here, it's decreasing there. Okay, so from at 1 is kind of the switch over between increasing and decreasing. So if it is decreasing and increasing, so if it's decreasing and increasing as it hits 1, what do we know is happening at 1? Is it a local min or local max? If it is decreasing and increasing, what's it doing? It's a local min. So that first piece of information there tells us when x is equal to 1, we need to have a local min on our graph. It has to be increasing always to the left and decreasing always to the right. Okay. Now, section 2 talks about concavity. Okay. So it says that it is concave up. It is concave up here and here. Our cup is up. It's concave up here and here. Okay. So it's 2 cups that are up. And this is the only spot in the graph where the cup is down. This is concave down. So between -2 and +2, the cup is down. I don't think it is. Oh, you left it open. Hey, thank you so much. Okay. Now let's take a look at bullet number 3. It says that the limit as x approaches -infinity. So this is saying that the left end heads to -2 and that the right end heads to 0. Okay. So the left end is heading to -2. I'm going to put just a little dashed line down here. And then the right end is heading to 0. I'm going to put a little dashed line right there, just to remind myself. And then at 1, I am going to put, it's a local minimum. So I'm going to put just a little dot. It's kind of down in our graph. Okay. Now, from it is concave up. It is concave, our cup is up. It is increasing. I'm thinking how to put all this together because these problems are evil. Okay, so it's increasing till we get to 1. It's always increasing. It's concave up and then concave down. So there's an inflection point at -2 and 2. So let's think. Okay, it's increasing but concave up. Okay. Increasing but concave up. Okay, so it's increasing, but the cup is up until we hit -2. And then our cup is down, but it's still increasing. Let's see. And then it's, our cup is down. That's so not right. Let's see. Our cup is up to there. Our cup is up to here. Our cup is down. Our cup is down. Okay, let's see. We're increasing. We have some, there's some issues with my graph. Let's see if I can. find. These problems are so bizarre to put all these things together. I want to see what I can do to make my graph prettier for you here. Oh, okay. Wait, is that the right graph? I'm going to come back to you on this graph. I really am. Because that is not correct. Okay, we'll come back. We will revisit this graph maybe tomorrow. Okay, let's do one where I can give you more information. Okay, so it says we've got this curve y equals x to the fourth minus 4x cubed with respect to concavity, points of inflection, local mins and max. Use this information to sketch the curve. Now I can do this one without a problem, so let me help you. Okay, so the first thing you want to do is you want to find your first derivative. You want to make a plus or minus chart for that, which will tell me the increasing, decreasing. This will also tell me the critical numbers. Plus or minus chart, increasing or decreasing, local mins or maxes. After you do the first derivative, you're going to kind of do it again. Then you're going to do the second derivative, which you need to find the critical numbers. You want to make a plus or minus chart. You want to find concavity from that. And you want to find inflection points. So they're kind of, the first four, we're going to do it simultaneously. The second four, we have we're going to do it together. So just lump those 4 steps together each time. Okay, so first thing we're going to do is we're going to find the first derivative, which is 4x cubed minus 12x squared. Now, the critical numbers of a first derivative are where the first derivative equals 0 or is undefined. So in this particular case, our critical numbers are always defined because it's a polynomial. So we just have to set that equal to 0 and see what happens. It is a factorable quantity. We can take out a 4x squared. If we factor out a 4x squared, we're left with x minus 3. So our critical numbers happen at 0 and at 3. So let's go ahead and make a plus or minus chart for our first derivative. So we know that it is equal to 0 in these 2 spots, and those are fine. Those are acceptable points. So I'm just going to put a dot there. I need some test values. So let's plug in -1, 1, and 4. Now, you really can plug it in to the 2-piece factored form or the entire original, both work. I tend to use the factored form as a guide. It's really kind of up to you. If you plug -1 into the 4x squared term, it's positive. +1 is still positive. 4 is positive. So a 4x squared term is always positive. Now, if I plug -1 into my x minus 3, I get a negative. If I plug in +1, I still get a negative. If I plug in 4, I get a positive. Now, those things are multiplied together, so let's multiply our plus minus. So a positive and a negative make a negative. Positive and a negative make a negative. Positive and positive make a positive. So 0 is not a change from increasing to decreasing. So it might be a critical number for the second derivative again. We'll see in a minute. But 3, if we have gone down and then gone up, it is a local minimum. So now we have everything we need from our first derivative. So now we're ready to look at our second derivative. If I take my second derivative, just take your first derivative, do it again. That's going to be 12x squared minus 24x. The critical numbers of our second derivative, again, just set it equal to 0. Or if it's undefined, this particular function, we don't have to worry about that. It is factorable. They're both divisible by 12, and they both contain an x, so take out a 12x. If you take out a 12x, you are left with x minus 2. So the critical numbers occur at 0 and 2. So what might that tell us? Well, if 0 or 2, there's a change in concavity. We call those inflection points. So they're allowed to equal 0. They're points on our graph, so we'll mark that. We're going to make a little plus minus chart. I need to include the 12x and the x minus 2. I'm going to plug in values. Let's plug in -1, 1, and 3. If I plug in -1, let's do the top row. If I plug in -1, I get a negative. If I plug in +1, I get a positive. If I plug in 3, I get a positive. Let's do the bottom row now. If I plug in -1 to x minus 2, I get a negative. +1 into x minus 2, I get a negative. +3 into x minus 2, I get a positive. Multiply those out, we get a positive and a negative and a positive. There is an inflection point at 2 places because we've changed concavity to concave up and concave down. We've changed concavity again there. So we have an inflection point at 0 and also at 2. Now, one of the things we need to get in the habit of doing is listing out the intervals of increasing and decreasing and the intervals of concave up and concave down. So let's go back to our first derivative for a moment. So our function is increasing when x is from 3 to infinity. It's decreasing in 2 intervals from -1 to 0, and then again from 0 to 3. Now you can include that whole thing, but 0 has this weird thing happening, so it's customary not to include it if it's a critical number. And we know that there's a local minimum at x equals 3. Now let's do the same thing for our second derivative chart. It is concave up wherever the second derivative is positive. That's from -infinity to 0. And then I see it's positive also from 2 to infinity. It is concave down wherever it is negative. So that's just in that center section from 0 to 2. And we have inflection points at 0 and 2. So that's everything we possibly know from the first and second derivative. First derivative gives us our increase and decrease in sections, local mids and maxes. Our second derivative gives our concavity, our shape of the graph, and any inflection points. Now, let's also talk about to graph it, because as we go through section 3.3, section 3.4, section 3.5, we are building upon the knowledge of the shape of a graph again and again and again for each of these sections. So anytime there's a strategy to graph things, okay, I'm going to kind of follow the same rules. The first thing you want to do is do the first derivative stuff. That's steps 1 through 4. Second thing we want to do is we want to do the second derivative stuff. Next thing we want to do is we want to find the x and y intercepts. Fourth thing we want to do is find the end behavior. So when they ask us to graph it, we're not done just because we've done the first derivative stuff and the second derivative stuff. We need to find the intercepts and the end behavior as well, okay? So let's go back into the function. Now let's look at our original function, which was y equals x to the fourth minus 4x cubed. By recognizing that it is a polynomial to the fourth degree, we know that if our degree is 4, the left end goes up and so does the right end. So polynomial end behavior is a nice thing. What does it do on the ends? As we go to infinity, it goes up. As we go to negative infinity, also goes up. Left and right ends go up. So just by pulling out that degree, we know that. But the intercepts can be a little bit trickier. For the intercepts, we need the original in factored form. So there is an x-intercept at 0 and at 4, because that factored form tells us that x equals 0 at 0 and x minus 4 equals 0 at 4. The y-intercept, if you plug in 0, you also get 0. So it has a y-intercept and an x-intercept. It goes through the origin. So if it has a x-intercept of 0, it will have a y-intercept of 0 as well. Okay, so now we know a lot more information about the graph. Let's think about some numbers we need. Okay, so we know it goes through the point 0, 0. It goes through the point 4, 0. Okay, those are the intercepts. Something happens at 3, we got a local min. Something happens at 2, we have an inflection point. So we're graphing the original. Let's plug 3 into the original. Let's plug 4 into the original. If we plug 3 into the original, we get, let's see, we get 81 minus 4 times 27. When you plug in 3, you get negative 27. Now remember, that's a local min. This is an intercept. This is an intercept. Let's plug in 2. If we plug in 2 to the original, we get 16 minus 4 times 8, or negative 16. That is an inflection point. Okay. So again, there's just so much stuff that we're trying to incorporate now. Okay. A lot of stuff. Okay. So now we're going to graph it. No, we're not. Use this information to sketch the graph. Yeah, okay. I did such a good one. Now this one I know, I have a lot more information. I know how to graph this one. Okay. So we need to definitely have 0, 2, 3, and 4. The lowest I see down is negative 27. So I'm just going to put negative 27, and I'm going to put negative 16 in some slightly tangible, but relatively, you know, I could have counted by 10s also in 20s, and I just put 16 and 27 on there. Okay. So let's put the points we know. We hit 0, 0. We hit 4, 0. At 3, we are down at negative 27. That is a local minimum. At 2, we have a change in concavity. At 0, we had a change in concavity. At 2, we are at negative 16. Okay. So we know the left end and right end goes up, and we know that it's concave up here. So our cup is up. So let's put that piece on. So it is decreasing there, and it is concave up. So it's going downhill, and it is concave up. There's a change in concavity at 0, and then it changes again. It's concave down between 0 and 2, and it is still decreasing from 0 to 2. But then it's concave up again, and that's the local min, and then it's going to keep going. So much easier to graph than the ones that we had before. So let's put everything together, okay? Let's check our graph. Does it check all the boxes? It is decreasing. Okay, so the left end goes up, right end goes up. That's our end behavior. We hit the x-axis at 0 and 4. We hit the y-axis at 0. We have a local min at x equals 3, the 0.3, negative 27. We are decreasing concave down, decreasing concave, decreasing concave up, decreasing concave down, decreasing concave up, increasing concave up for the rest of eternity. So there you go. So we have everything put together. So back in pre-calc, we wouldn't necessarily have known how far down that went. We wouldn't have known that that had to curve like that. We would have just kind of put it on there, and we wouldn't have really said the curvature of it. So that's where, again, we're putting the things we have together. We're blending the stuff from pre-calc. You know, so I still had to do the intercepts and the end behavior that I learned in pre-calc, but I still had so many more extra little things that I never knew before. Okay, so again, these take a lot of work and thought. You know, they are what they are. Okay. Now, in example 7, there's going to be times where I will actually give you the first and second derivative when they're disgusting. Let's assume these are powers. I use the function editor that was in there, but it's very disgusting. But those are the derivatives. So we've done that for that particular equation. Okay. So we're going to start exactly like we did before. We're going to start with the first derivative. We're going to go to the second derivative. We're going to look at the function. We're going to do all that stuff, okay? So our first derivative, a fraction equals 0 where the top equals 0. So in this case at 4. But a fraction can be undefined where the bottom equals 0. So I also need the fact that we do have some funky points, a critical number at 0 and at 6. Now, these are not critical points because they're not points on the graph. They might not exist in the original function. They might. So let's check them actually before I cross them out. Can we plug 0 into the original? Yes. Can we plug 6 into the original? Yes, actually. Those are points. So let's put those on a number line from least to greatest order. I am going to plug into each individual piece. So I've got that 4 minus x in the top. I've got an x to the 1/3. That does say x to the 1/3. Sorry, it's so gross. And then 6 minus x to the 2/3. And then I'm going to plug in some values. So I'm going to plug in -1, 1, 5, and 7. I'm just going to start with the top value. If I plug in -1, I get 7 to the 2/3 power is still going to be a positive. I don't care what that number is. I don't know. If I plug in 1, I get a positive to the 2/3 power is a positive. If I plug in 5, I get 1 to a positive power, which is still a positive. Now, here's the one that's weird. If you plug in negative or 7, you get -1 in parentheses. But let's think about what a 2/3 power means. A 2/3 power, the 2 is going to square it. The 3 is going to take the cube root of that. So if I square a -1, it's going to become a positive, right? And then cube root it, it's still going to be a positive. So this is a function that is always positive. And if you were to graph 6 minus x to the 2/3, it is just a positive thing. That square made it positive. Okay, now let's plug in to this middle section here. Okay, if we plug in -1, I get a negative. Cube root of that's a negative. If I plug in 1, I get positive. If I plug in 5, I get a positive. If I plug in 7, I get a positive. So those are good. Now let's plug into 4 minus x. If I plug in -1, I get a positive. Positive 1's a positive. 5 is a negative. 7 is a negative. Now, let's think about the fact those are multiplied or divide. One negative stays negative, all positives, negative, negative. So we know right now from our first derivative, it goes down then up. So that is a local minimum. It goes up then down. That is a local maximum. It doesn't, it just kind of goes through it. I'm suspecting maybe that that's an inflection point, but if it is, it'll rear its head again in the second derivative. So it is decreasing from -infinity to 0, and then from 4 to, we'll just go 4 to infinity for the room's sake. Okay, it is increasing only from 0 to 4. Okay, now we're ready to do our second derivative, I guess. Now we have the functions been given to us. So the top doesn't provide any numbers. We see very similar things that we did before. So we have critical numbers at 0 and at 6 again. So we have to put on there 0 and 6. Now include your -8. Yes, it's always negative, but include that in your mathematics. And then we have x to the 4/3 and 6 minus x to the 5/3. So I'm going to plug in -1, 1, and 7. Okay, so if I plug -1 into the top, that 4th power is going to forfeit. It's going to make it positive. If I plug in 1, positive, 7, positive, always positive. But a 5/3 power doesn't do that. The 5th power doesn't change a sign. So whatever we get, we get. So 6 minus -1 is 7. That's a positive. 6 minus 1 is positive. 7 minus 1 is a negative. It's going to stay negative throughout that process. Okay, so we have 1 negative, 1 negative. 0 isn't a point of inflection. But 6 is, you'll notice that this is a change in concavity. So that is an inflection point. Okay. Now, like any function, now we have to do the third thing, unfortunately. What's the actual function doing? So we have to revisit the actual function. So we analyze the first derivative, analyze the second derivative, and then we need some points and some extra little pieces and parts that the first or the original function gives us. Okay. If we look at the lead term, and it's kind of hard to picture this, but it's almost like if you took an x to the 2/3 times a negative x to the 1/3. If you distribute, think about if you distributed, wouldn't you get a negative x? What does a linear function do that has a negative coefficient? It's a slope down, right? Okay, so it's just going down. So I believe the left end goes up and the right end goes down based upon my lovely, pieces of information. What other things do we need? I see things happening at 0, 4, and 6. So I better plug in 0, 4, and 6. Something happened there. Okay. Well, 0 is at 0. 0 is an xy intercept. 6 is a intercept. So we don't have to search for the intercepts. What happens at 4? Well, 4 to the 2/3 power times 2 to the 1/3 power, I believe, is 2. But I'm going to tell you that in a minute. No, it's not. It would be 2 to the 4/3 plus 1/3, 5/3. It's a gross decimal, so let me tell you what the decimal is. I thought it was going to be something nice, but it's not. So it's about 3.17. Okay. So what about the concavity? It's concave down from negative infinity up to 0, and then from 0 to 6. It's concave up from 6 to infinity. Okay, so let's put all these gross pieces together before this bell rings. At 0, I'm at 0. At 4, I'm at 3.17. At 6, I'm at 0. Okay. Now remember, we found a local max. So let's put a max next to that little word right there. And this is an inflection point. 6 was an inflection point. Okay, so it's concave down. Oh, 0 is the local min. Concave down. It's concave down all the way until we hit 6. So there's a little bump there. And then from 6 past, it is concave up. So 6 is an inflection point. It's concave up, but it's still going downward. So it's kind of like that. The little cup is up. Okay, so look, cup is down, cup is down. Cup is up. Local min, local max, inflection point. Concave up, concave down, or concave down, concave up. So that is what that graph looks like. Isn't that just too beautiful for words? So don't expect that this homework is going to be quick. It is not. So we're going to be working on it tomorrow during class, maybe even the next day. This is a section that's going to take a while. And then 3, 4 will go a little quicker because we're adding limits to infinity and some asymptote stuff, so that 3, 5 becomes everything and can be very disgusting. Okay? Yeah, because now we're going to put all those pieces together. So we might have horizontal asymptotes, vertical asymptotes, other pieces and parts too. So this is what we're going to do tomorrow in class. We're going to work on this stuff. So if you need anything, you can ask questions as you go. Okay, so there you go.